Hello. So in the last video we explored time dilation, and now we're going to look at another effect called length contraction. So let's suppose we have a rod and we'd like to measure the length of this rod, and we're going to measure its length in two different frames of reference. The first frame of reference, which we're going to call S, is the frame of reference in which the rod isn't moving. We call this the rest frame of the rod. The second frame of reference, S prime, as always is going to be moving at speed u relative to s. So for somebody in S prime, the rod is moving backwards to the left at speed u. So this is the frame in which the rod's moving. Now to measure the length of something, what we need to do is look at both ends of that object, measure the locations of both ends, take the difference between them, and that's the length of the object. So let's look at doing this first in frame S. So to make things nice and simple, we'll choose that the left-hand side of the rod, we'll call this end 1. This is at position 0 when they make their measurement. So that is x1 is equal to 0. And we'll say they make their measurement of this end of the rod's position at time 0, so t1 is 0. The position of the other end of the rod, let's call that n2, that is going to be the length of the rod as measured by S. I'm going to call that length L0. We're going to call this the proper length of the rod. So this is the length of the rod measured in its rest frame, the frame where it's not moving. And we don't care when we make the measurement of the other end of the rod's position. It's not moving, so it's always going to be at the same place. Now let's think what happens in frame S prime. So as always, we set up our frames of reference so that at time 0, S prime is exactly on top of S. So S prime is going to agree on the location of the first end of the rod, end 1. So x1 prime is going to be 0. And they're also going to agree on the time that that measurement was made. So t1 prime is also going to be 0. Now the location they measure for the other end of the rod, x2 prime, well that's going to be the length of the rod that they measure. So let's call that something different, let's call that L. And then finally we have to think about the time that they're going to make that measurement, t2 prime. For somebody in S prime, the rod is moving. So in order for them to think that the length of the rod has been correctly measured, they must say that the measurements of position 1 and position 2, i.e. the positions of the two ends of the rod, they have to be made at exactly the same time. So from their point of view, t2 prime must be equal to t1 prime. So this must also be equal to 0. So this wasn't a constraint we had for S, because for S, the rod isn't moving. They don't care that the measurements were made at the same point in time. Okay, so now let's use one of the Lorentz transformations to see if we can figure out a relationship between L and L0. So in general, we have that x is equal to gamma into x prime plus ut prime. So if we apply this to the measurement of the second end of the rod, the right-hand end of the rod, we would have that x2 is equal to gamma into x2 prime plus u times t2 prime. t2 prime, we've said, is 0, so we simply have that x2 is equal to gamma x2 prime. And then substituting in what x2 and x2 prime are, we have that L0 is equal to gamma L, or the way we normally write that is that L equals L0 over gamma. This is the length contraction equation. What it says is that if we have a rod of proper length L0, meaning if you're not moving relative to the rod and you measure its length, you're going to measure L0. Then somebody who is moving relative to the rod with some speed u is going to measure a length L, where L is given by L0 over gamma, and gamma has the normal meaning, it's the square root of 1 over 1 minus u squared, so the speed squared, divided by c squared. So we should be clear why this is happening. For the observer in frame S prime, it's critical that they say that the locations of both ends of the rod are measured at the same time. That is, t1 prime is 0, t2 prime is 0. This doesn't matter for S. S doesn't have to insist that those measurements were both made at the same time, because for their point of view the rod isn't moving, so it makes no difference. And in fact we could figure out what time does S think the other end of the rod's position was measured. So we could write that t2 equals gamma into t2 prime plus ux2 prime over c squared. So this is the Lorentz transformation for time applied to the second event. Now t2 prime is 0. The observer in S prime says that both measurements were made at time 0, so that's 0. But x2 prime is not 0, that's the location of the other end of the rod, that's L. So we have that T2 is equal to gamma u L over c squared. And this is not equal to 0. So gamma is obviously not equal to 0, u, the speed, is not equal to 0, and the length of the rod is not equal to 0, so this is not equal to 0. Or to put it another way, it's not equal to T2 prime. And it's also not equal to T1, which is 0. So the observer in frame S says that the two ends of the rod were measured at different times. The observer in S prime says they were measured at the same time. And that's why they disagree on the length of the rod. So this idea that two observers don't agree on whether two things are simultaneous or not, as in whether both ends of the rod were measured at the same time or not, this is called the relativity of simultaneity. And we're going to come back to this in later videos. We can explore this further using something called the ladder paradox. So the idea is that we have a farmer and he has a ladder that's 10 meters long. And he would like to put his 10-meter long ladder inside his barn. Unfortunately, the barn is only 5 meters long, so it doesn't fit. So what he decides to do is to take his ladder and he's going to accelerate it up to some high speed u such that gamma is equal to 2. And now from length contraction, L equals L naught over gamma, his ladder will be shortened to 5 meters. So he watches his ladder shoot off at this high speed. It goes in through one door of the barn here. Just as the front of the ladder gets to the other side of the barn, he closes both this door, and momentarily the ladder is inside the barn. Now the ladder has to carry on moving, so we still have this length contraction effect, so he can then immediately open both of the barn doors and the ladder can carry on its way. But for that moment in time, the ladder fits inside the barn. Now, let's suppose that the farmer's wife is sitting on the ladder. Now she's in the rest frame of the ladder, so she doesn't see the ladder length contracted. She always says it has a length of 10 meters. However, from her point of view, the barn is rushing towards her at speed u. So she sees the barn length contracted to be only 2.5 meters long. So from her point of view, the situation seems even more hopeless. Now the farmer is trying to fit a 10-meter ladder into a 2.5 meter long barn. But if the farmer is going to close both of the doors when he thinks the ladder is inside the barn, that's something physical. If the ladder does not fit inside the barn, at that moment he's going to chop off the ends of his ladder. He doesn't see that happen, but how can we explain that the farmer's wife doesn't see that happen? So this brings us back to the idea of the relativity of simultaneity. So what's the farmer's wife actually going to see? Now remember, to start with, both doors of the barn are open. She's going to see the barn rushing towards her. The ladder goes into the barn just up to the point where the front of the ladder reaches the back door of the barn. At this moment, the farmer is going to instantaneously close this door and then open it again. The ladder, of course, will carry on moving. At some point, the back of the ladder will be just inside the barn, and at this moment, that's when the farmer is going to close and then reopen this back door. So the point of disagreement here is that the farmer thinks he closed and opened those two doors simultaneously. And because he thinks he did that, he thinks the ladder must have fit inside the barn. But the farmer's wife says, no, you closed and opened those two doors at different moments in time. So the ladder actually never fit inside the barn. So we have two different ways of describing the same physical outcome. The ladder doesn't get destroyed, but really two quite different viewpoints on why that happened. So next time we're going to talk more about this idea of the relativity of simultaneity and start to develop our understanding of something which we call space-time. Please don't forget to subscribe, and I'll see you soon.